we are making a differentiator. First I have taken an op amp and then I've taken offset voltages of plus 12 and minus 12 and I've taken ground also. So this is ground and this is minus 4 and this is plus 4. So I'm taking a signal input of a sine wave from the signal generator of 1 kilohertz and 1 volt peak to peak. So I'm taking an input and the other end to the ground, and then I'll collect a capacitor in the series. To the inverting end of the op amp here, and then I'll connect a feedback resistor to the op amp. So feedback resistor generally is connected from the inverting input to the output. So output part of the op amp is at 6. So from the last, it's second one, I'm connecting to the output. This is the feedback resistor connected. And then I have to take the non-inverting input to the ground. This is the non-inverting input, third one, to the ground. Then generally I'll take output for the oscilloscope. This is the output. I'm taking the output and the other end to the ground. So this is the final circuit of the differentiator. I've just taken a capacitor of 100 nanofarads and 1 kilo ohms of feedback resistance, connected the inverting and the output, and this is the ground.
So this is a differentiator circuit and it is a high pass filter, and its dB gain is anti-log V out upon V in. And when we are changing its frequency, like we can see here, when the frequency is 1 kilohertz, the output voltage is 216 MV, and when we are changing the frequency to 1500, its output voltage is changing to 318 MV. So we can say then when we change the frequency, its output voltage is increasing. So for the differentiator circuit, the formula of voltage out is minus RC dVi upon dt. As we can see, the formula of dB gain is 20 log V out upon V input. So as we change the V input, the V output is increasing, and as the frequency is increasing, a dB gain is increasing as shown in the figure. And this graph is for both two different resistors, and this one is 1 kilo ohm and this one is for 2.7 kilo ohm.
So the formula for the gain is minus RC j omega for the differentiator. And so we can check the gain is directly proportional to R. Okay, so we'll see that the first curve, the blue one, is for 2.7 kilo ohms and the orange one is for 1 kilo ohm. So as we increase the resistor's value, we get a higher dB gain, and if we decrease it, we get a lower dB gain. So we can see that this is the on the y-axis we have the dB gain, and on the x-axis we have the log values of the V out of the frequency. So we can get we can see this is a high pass filter. For high values, it passes the voltages quite easily.
So we have done it for the sine wave. Now we will do it for the square wave. So when I change the input to the square wave, this will be the input and output. So when the differentiator generally differentiates the input, so this when when there is a constant thing in the square wave, then there is no the differentiation of a constant is 0, so it is showing 0. And then when it's sudden change in the graph, then we'll see a spike because of the change, which is slope, and that is itself the differentiation. So these are the spikes where the sudden changes occur in the square wave. So uh, I've already set the op-amp circuit. I've taken the offset inputs. I've set the ground, and I've already taken this input from the signal generator and taken output for the oscilloscope. And now we are making circuit for the integrator. So for the integrator, for the general op-amp inverting circuit, we'll have a feedback resistor. So there we'll just replace the feedback resistor to a capacitor of 100 nanofarad. I'm taking an 100 nanofarad capacitor, and I'll place it in the I'll replace it with the feedback resistor placed. So this is the input, non-inverting, inverting input, and I'll connect it to the output. This will be the feedback. Here I've done it, and then I've just take a resistor to the in the series with the input. This is the input circuit from signal generator, and I'll take it from the input. So this is the integrator circuit.
This is the graph of the dB gain versus frequency for the integrator circuit. The upper curve, blue one, is for 1 kilo ohm resistor, and the below one is for 2.7 kilo ohm resistor. As in the dB gain for the integrator circuit, it is 1 by RC. As the as the resistance increases, the gain decreases. Also, we can see that the V out will decrease. We have the formula V out for this integrator circuit, which is 1 by RC integration of Vi dt, and the negative sign is over here. We can check this using the oscilloscope. Like for the 500 hertz, we are using 1 kilo ohm resistor. So initially for this frequency, we have a very high output, peak to peak value 8.64 around here. And as I increase the frequency to 1 kilohertz, see how it has changed, how drastically it has changed to 4.4 volts peak to peak. Let's see the values in between those. Okay. I have 500 hertz again, and I change it to 600. So for 600 hertz, it has changed to 7.2. Now it's 700 hertz, it is 6.24 volts. For 800, 5.44. So we can see it is decreasing, and when we take the log values, we get something like this curve. Yeah. So this is a low pass filter integrator circuit, because for the low values of frequency, it has a high dB gain.
Wave inputs. So we have designed something like this. So first we have taken an adder circuit, means a summing circuit. In that, and we have connected a series circuit of a general inverting op-amp with it. So generally it works like this. Means the general output of a V output of an adding circuit is something like this: RF by R1 V1 plus RF by R2 V2 whole multiplied by the minus. And then for this general op-amp which is inverting, the output will be like this: minus RF by R into V input. So the logic here is, first this adder circuit generally adds two sine waves V1 plus V2, but we have a negative sign in front of it after the output. So we'll generally give this output to a general op-amp inverting circuit, where we have 2R as the series resistance and a feedback of R. So generally this gives an output of something like this. So V out is the input V1 plus V2 into minus, and then this feedback resistance by the 2R, and there will be a negative for this output also. So negative negative cancels, and we'll get V1 plus V2 by 2, which is the average output of the two sine waves we have given. So generally this is the circuit we have designed. So we have applied it to the breadboard in the real case. So these two are the this and this is the two sine waves here again from the circuit sine wave generator. So we've given 1 kilohertz and with 1 volt peak to peak for one sine wave, and then 3 kilohertz and 500 volts peak to peak for another sine wave, and the output we have got is something like this.
Okay, so we have in channel 1 input of 1 kilohertz and 1 volt peak to peak as given in the question, and in channel 2 we have 3 kilohertz and 0.5 volts peak to peak value, and we get an output of the two sine waves average like this. And if we check the FFT for this, let me scale it up. Yeah, we get this value. So the first one should come around 1 kilohertz and the second one should come around 3 kilohertz. So let me just check frequency. Yeah, so I have the cursor on the first peak. Yeah, and we get see, it is almost 990 hertz. If we check, yeah, 1 kilohertz, and if we move the cursor to the next peak, this is the FFT view of the signal we have got as the output. And let's check the cursor frequency. The first peak should come around 1 kilohertz and the second should come around 3 kilohertz. So let's move the cursor and check. Yes, we see that the first peak is at 1 kilohertz frequency, and I move it to the second peak. Yeah, I got the 3 kilohertz frequency. So idea for this question, we got the correct output. We got the correct output, and let's for the phase thing, let's come here. For channel 1 the phase is 36. We have put 36 because it has some inherited phase shift due to the oscilloscope and the cables. For zero phase we have the output like this, but if we bring it to the correct values, it comes out to be like this, which is the summation of the two sine waves we have been given. For the second channel we have zero phase, so the total phase difference is 36. In general the phase shift should be 0. Phase of the oscilloscope we have given 36.
Explaining third question circuit. So here we have V1 signal and V2 signal. The resistance used in this circuit throughout is R, and it is connected to inverting terminal of op-amp. And here R feedback is also same value as resistance used in V1 and V2, and the positive terminal is grounded. So up to this is the V out 1, which is summing op amp, and after that we connect two R valued resistance, and then we connect it to op amp, invert terminal of op amp, and R feedback here is used of value R, and we get V out. So V out 1 is R feedback into V1R plus V2R, and it is V1 negative off, and V out is this is V out is here we are grounding the positive terminal of op amp, and V out is minus of R V1 plus V2 by 2R, which is minus of, which is V1 plus V2 by 2. It is average of V1 and V2. So the op amp